In this video, we're going to orthogonally diagonalize a symmetric matrix. We learned in the fundamental theorem of symmetric matrices that a symmetric matrix is orthogonally diagonalizable. And A is a symmetric matrix, you can see right there. And we're going to orthogonally diagonalize it. So we're going to start by just doing the procedure we learned for diagonalizing. And once we've done that, we're going to just make it... we're going to make it normal, and you'll see what that means. Normal means, in this context, it means turn the vectors into unit vectors. Anyway, let's proceed. So let's just get a regular diagonalizing matrix as follows. So first we look at the characteristic polynomial, and that's going to be lambda minus -2, lambda minus +2, lambda minus +2, and then lambda minus -2. Lambda minus 1, and then you subtract -2 and minus... so you know how to do this. We've done this a bunch of times. Anyway, when we multiply this out, we get lambda squared plus lambda minus 6, which factors into lambda plus 3. Lambda minus 2 equals 0, and that gives us our two eigenvalues, and that's lambda 1 is -3, and lambda 2 is +2. And we're going to use those two eigenvalues to get our eigenvectors. And here's how we're going to do the first one. We're going to plug in lambda 1 equals -3, and we get this matrix, which is equal to that, which reduces down to this, which yields this eigenvector right here, -2, 1. And then we're going to do lambda 2 equals 2. We're going to plug 2 in for lambda, which gives us this matrix, which reduces down to this matrix, which gives us this eigenvector. And now, our two eigenvectors. Now, these two eigenvectors will indeed diagonalize matrix A if we make these two vectors columns of a matrix P. But we want to do more than that. We want it to be orthonormal. We need to turn each of these vectors into a unit vector, and to do that, we just divide by the magnitude. So P1 is going to equal our first vector, just divided by the magnitude. The magnitude winds up being square root of 5. So instead of -2, 1, it's -2 over rad 5, 1 over rad 5, because it's just rad 5ing everything. And P2 is going to be the same vector, but it's divided by the magnitude of the second vector, which is also rad 5. So it's 1 over rad 5, comma 2 over rad 5. That's my P1 and my P2. And all I got to do is take the P1 and P2, combine them as column vectors to construct our matrix P, which is the matrix that we're looking for. So here's our matrix P right there. I just took these two vectors and made them columns of our matrix P, and I just want to test that this works. And I want to show that P inverse AP, which is going to be better be equal to P transpose AP, is equal to this. That's P inverse. That's A. That's P. That's P. Notice that P inverse and P really want to be the same thing, because P transpose is P. P is turns out to be diagonal, and when you multiply all this together, and I want you to do that, you're going to get -3002, and which is of course a diagonal matrix. Yay!